Okay, greetings, aspiring scientists. Welcome back. If you're coming from one of my other videos, if you're here for the first time, then welcome. I'm so excited today because today is really the first lesson that's really about chemistry. Not that math and science communication aren't important, but today we can actually start to discuss some of the properties of the world and the universe that we live in, which is really exciting. So we're going to start very basic and near the beginning, and what really is the beginning of the IB chemistry curriculum, but this should apply to all high school and many, first year university curriculums as well. So, at the end of my last video, I had a few points that I said we should consider just before we really jump in, so I'll go through these really quickly again. So chemistry is the study of energy transfer between small particles. And nature tends towards low energy states. If a system is high energy, try to think about the reason. If you're unsure about what will happen, think about how a system could reduce its energy. So we start with structure, the first half of the curriculum and the first half of the textbook that I'm mainly using, which is the introduction to the particulate nature of matter. And the way that the IB curriculum is set up is each of these sections has a guiding question. So our guiding question here is, how can we model the particulate nature of matter? And the idea of modeling is quite an important idea in science and in the IB science curriculum. It's basically we can't really directly work with atoms and molecules and energy transfer on the quantum scale. So we need ways to model it with mathematics, with analogies, with those kind of things. So this is the question: how do we model the particulate nature of matter? The idea that matter and things are made up of small particles, microscopic particles. So hopefully we'll be able to answer this by the end of this unit and by the end of this video. So we start with 1.1.1, the composition of matter. So fundamental ideas. Matter first. What is matter? So parts of the universe that are made of particles that have a mass. Mass is a property that we measure in kilograms. They occupy space. We measure in meters cubed usually, and they're in constant motion as well. Doesn't necessarily mean that they're moving from right to left or left to right, but many of them are just vibrating in place. I think that's a property of matter as well. So things that are not matter are usually some form of energy or some form of radiation or field, or they're human ideas like, love and responsibility and humor, those kind of things that are not really existing in the universe that we observe. Okay, atomic theory then. This is the theory that all matter can be broken down into fundamental particles called atoms. Atoms are unable to undergo further breakdown through chemical reactions or chemical transformations. So that's an important idea. You might have heard of things that are smaller than atoms, like protons, neutrons, quarks, whatever. Those do exist, but atomic theory is the idea that through chemical reactions, sort of the movement and sharing of electrons, through those processes, we cannot break down particles any further, or when we cannot, we call those things atoms. Elements then are particular atoms with unique properties based on their subatomic composition, and they are essentially the building blocks of nature. So try to use any vocabulary that I introduce to you in any explanations that you give for practice questions and exam questions. So more fundamental ideas. An elementary substance, or a pure element. So a sample of matter that contains only one pure element is called an elementary substance. Those atoms may be chemically bonded to themselves or not. And I think it usually must be greater than 95 to 99% pure to have a classification of a pure element. I sort of just pulled that number out of nowhere, but that's my image of a pure element. Every field and different area of science and work probably has their own definition of what percentage it must be to actually be pure. But we're almost never going to get a 100% pure sample unless we're dealing with very small amounts of atoms, which I think is very rare. So next, element symbols. This is a short labeling system that can be found on the periodic table, which can be found in your data book and probably in your textbook or anywhere online. So each individual element has a 1 or 2 letter code, and the first letter is always a capital. The second will be a lowercase, if there is a second. So I have a little snapshot of the periodic table from the IB chemistry data book. You can see various elements and their symbols here. H for hydrogen, Li for lithium, Be for beryllium, and so on. But this is just a small section of that. The real periodic table is much larger, as I'm sure you know. But I do want to point out that you need to be a little bit careful. You might think you'll never make a mistake like this, but consider something like C little o and C big O. You can't make mistakes when you write these, okay? C little o is cobalt, a particular element, whereas CO, both uppercase, big C, big O, is a chemical compound, a bond between carbon and oxygen, carbon monoxide. So you really do have to follow the actual element symbols that are on the periodic table. Alright, so a compound, or a chemical compound, is a sample of matter that contains multiple different elements chemically bonded together. Now, it's going to be a while before we discuss in my videos and in the curriculum what a chemical bond really is, but for now, just be aware that different elements and atoms can bond together. So if there are different elements bonded together, notice this is not the same element, that would still be a pure element. But different elements chemically bonded together form a compound. Then a chemical formula. This is the symbol of a chemical compound, and it's simply composed of the element symbols of each element contained. However, they may have numbers if there are multiple amount of the same element within a compound. So here's some of my Google Gemini generated images for compounds that you probably know. CO2 for carbon dioxide. So there's 2 oxygens in that, 1 carbon. H2O, very familiar, water. That's 2 hydrogens, 1 oxygen. And H2SO4, you might have heard of, is a strong acid, sulfuric acid. So 2 hydrogens, 1 sulfur, 4 oxygens. Okay, some more discussions about these. So elements contain atoms of only one type. For example, Ne, neon, or H2, hydrogen. And I've got some generated images of these gases in a container here. So neon, the yellow, these are just neon. And it's like a ball atom you can consider. They're not bonded to anything, including themselves. But H2 is also a pure element. These are classified as the same, but molecules have a chemical bond, at least one. So these are H2 molecules. They have a bond between an H and an H. But they're still only H, so they are classified as a pure element, or an elementary substance. On the other hand, compounds contain a combination of atom types. Example, CO2, carbon dioxide, H2O. And I have a couple ChatGPT images here, but this is basically exactly what CO2 and H2O look like in most bonding or drawing conventions. Alright, then mixtures. mixtures contain two or more pure elements or compounds. For example, salt water. So here's a depiction of water, H2O, but someone has dissolved, or something has dissolved salt, NaCl, inside of here. So we've got Cl minus ions. An ion is a charged, an electrically charged version of an atom. And then we have sodium Na, little ions in there as well. So this whole thing is a mixture. There is H2O, which is a chemical compound, but there are chloride and sodium ions in this as well, causing it to no longer be a pure compound, but it's a mixture. But the Cl and the Na are not chemically bonded to the waters, so they're not technically a compound that contains water and chloride and sodium. They're just mixed together, dissolved. So mixtures, we can separate these into two categories as well, homogeneous or heterogeneous. If you know some Latin, you might know homo means same and hetero means different. So there's something the same about homogeneous solutions and something different about heterogeneous. So homogeneous mixtures, they have what's called even distribution, uniform distribution. So this means that you cannot easily identify different components within them. And a good way to think about this is if you took any random chunk or small sample of your whole mixture, there should be even spreading of each component of that mixture. So if I had salt and water, and I took any particular small region of my sample, I should have basically equal spreading out of water molecules and salt ions. If they are not so, then they are not properly mixed and they're not a homogeneous mixture. So some examples of things that I think are homogeneous mixtures are well-mixed metal alloys, like I have in the picture here on the left. Maybe that's like a bronze alloy, very shiny though, but evenly spread out different types of metals to make an alloy. Something like a juice or a soda. So I have a picture here of a cup of ginger ale. I think the actual liquid of ginger ale is a homogeneous solution, but you can see there's little bubbles in there. As soon as you have those bubbles, actually this is no longer a homogeneous mixture because there's a phase difference between liquid and gas. That's going to mean it's more of a heterogeneous mixture, but the actual, if this was not carbonated, the ginger ale part, I think, is a homogeneous mixture of some sugar and some acid and some flavors and water. And then in the back, we have a transparent balloon. This contains some kind of air or gas. But gases, given enough time, will spread out and equally fill that container and become a homogeneous solution. Any small section you take contains sort of the same proportion and the same spreading out of whatever different gases are inside. Okay. What about heterogeneous then? Heterogeneous mixtures are not evenly distributed. You can identify different components in different areas. So you can think of a lot of different foods like, chicken soup. If you take a particular chunk or volume of this bowl of soup, it's going to have, parts of chicken, parts of noodles, parts of broth, not evenly distributed. Something like sand, although this picture looks like it's pretty fine and homogeneous sand, most types of sand are a various mixture of rocks and minerals and dirt and organics and many different things. They're not homogeneous. Something like bubble tea, similar to the previous example, we have more solid chunks of tapioca inside of this liquid kind of milky substance. Any way you look at it, not homogeneous, so it's heterogeneous. My Google Gemini also generated some very weird kind of cauliflower dough looking thing in the back. No idea what that is, but I think it belongs on this slide because it's probably a heterogeneous mixture. Those things are not evenly distributed. You can tell by the little color patches. So, matter in summary, here's a little flowchart. Matter has mass and occupies space and is probably in motion, some vibration of its particles at least. So, a pure substance has a definite composition of one element or compound. Then you can break that into pure elements and pure compounds. Pure elements, all particles belong to one particular type of element. Pure compound, all particles are a particular combination of two or more elements. And one chemical formula, basically. On the other hand, a mixture is a combination of two or more pure substances. They could be pure elements or compounds, but when they're mixed and not chemically bonded, that's a mixture. Then if they're evenly distributed, it's a homogeneous mixture. If they are not evenly distributed, there's different areas with varying proportions due to non-uniform distribution. That's a heterogeneous mixture. Okay, something I'd like to make clear is the difference between physical and chemical changes or processes. So physical change or physical process, a change where no new chemical bonds which result in a change of chemical formula are broken or formed. Those chemical bonds are not broken or formed. Okay, I added in this part about no change in a chemical formula because I did look up some examples. For example, like a piece of coal or charcoal, mostly carbon, changing into diamond under high pressure and temperature. There are some changes in the bonding between those, going from like double or single bonds into a different geometry and more single bonds. So I think that process is still a physical process. There's been no new chemical bonds between different elements, but there may have been chemical bonds changed or shifted between carbon atoms, like the same element. So even that case, I think, is considered a physical change. But that's kind of an exception that maybe we'll discuss in the far future. Anyway, chemical change is a change where new chemical bonds, which result in a change in chemical formula, are broken or are formed. So something like O2 and H2 coming together to form H2O, that's a chemical change. So, another flowchart to go through the different categorizations of matter. Matter has mass and occupies space. You can ask the question, does it have uniform distribution? If the answer is no, it's immediately a heterogeneous mixture. Different areas have varying proportions due to non-uniform distribution. And that's because, like, a pure element or pure compound can't really have non-uniform distribution. As far as I know, there might be a couple examples I could think of where there's like different types of crystals in a pure metal or something, and it's not completely uniform. But again, that's an exception. Alright, so if the answer to does it have uniform distribution is yes, then you can ask, can it be separated by physical methods? For example, distillation or filtration. If the answer is yes, it's a homogeneous mixture. All particles are evenly distributed. If the answer is no, it can't be separated by any physical methods. Then you have to ask, can it be separated by chemical methods? For example, hydrolysis or, I don't know, something like combustion. If the answer is yes, then you have a pure compound. Okay, something like H2O. If you have pure H2O, there are chemical ways to separate H from O. For example, hydrolysis, that's inputting electrical energy to break apart all of the H and O bonds and send them back into pure elements. If your answer is no, though, you have basically a pure element. All the particles must belong to one single type of element. But you really have to try to break the chemical bonds as much as possible with electricity or heat or something. And if you really cannot, you have a pure element. moving on. Practice question. A student finds 2 different jars in the laboratory cabinet of their school or of their institution. They're not labeled, but both contain a fine white powder. No idea what that is. The student decides to do an experiment. He heats up 50 grams of both powders in separate containers in some kind of oven to 100 degrees Celsius. Both powders turn to a dark shade of brown color. Can the student conclude that both jars contain the same substance? White powder turns to brown powder. So you can think about that for a minute, but I think it should be pretty obvious. The student cannot conclude this, and that's because there's nearly unlimited amounts of compounds that are a brown powder, right? Just the fact that these 2 white powders made the same color change can't really tell you that this product or that the starting materials were the same in each case. If they had turned a different color, what could they conclude? Well, they can't even conclude much from that. I think that provides some evidence that the 2 starting materials, the white powders, are not the same. Assuming they were heated in the exact same way, they seem to have produced 2 different products that have 2 different colors. But you really need more evidence than these kind of things to say such confident statements as these 2 substances are the same or not. Another situation then, a student suspects that a block of wood is a pure element. Not the brightest student on the planet, but she puts the wood in a vacuum chamber, heats it up to 300 degrees Celsius for 3 hours. The wood changes from a dense wood-like object into a low-density, porous, jet black material. What can the student conclude about this object? So is this a pure element? Well, it really seems to have undergone a chemical change. A color change is usually indicative of a chemical change, and it's also seemingly lost mass if it's less dense now. Maybe the vacuum pulled away some things that were vaporized. What might she have learned if there were no change? So if it didn't change at all, that would be some evidence that this cannot be broken down through chemical change. 300 degrees is enough for quite a few chemical changes to happen, but not all of them, okay? She would really need to heat this up to thousands of degrees, beyond sort of the melting and boiling points of various metals or any type of compound, to really have good evidence that chemical change cannot be done on this substance. Okay, so it's a bit of evidence, but not conclusive that wood could be a pure element if there were no change. Anyway, separating mixtures. How do we separate mixtures? And you might ask, why would we care? Well, we often want pure starting materials for many things, for scientific research, for industrial processes. If you go to your lab and you're going to do your IA or some kind of practical experiment and you need, copper metal, you order it from a company. If what they send you is like 70% copper or less, you might be pretty annoyed because you're trying to design your experiment based on what happens with copper in a reaction. And then that company would lose its reputation as a provider of chemicals. So, they have an interest to get things as pure as possible while still being economically viable. So separating elements and compounds is of great interest to many scientists. Mixtures are usually messy and difficult to work with and predict. Separation must take advantages of differences between the compounds and pure elements. So you could try to think of what properties substances might have that allow us to separate them from others, but here's my list of a couple things. Magnetism. Some metals like iron and nickel, I think, are magnetic in the sense that they're attracted to parts of magnetic fields. Weight. Different compounds and elements have different mass and therefore weight in Earth's gravitational field here. Solubility. Some things will dissolve in water or other substances, other liquids, to varying degrees. We can take advantage of that. Boiling and melting points, this is a huge one. Things will change state and therefore behave differently and flow differently at different temperatures. We can take advantage of that as well. Chemical reactions. So some elements and compounds will only chemically react with certain other compounds or elements under specific conditions. And if we react them in that way, they can leave behind other parts of a mixture, which we can take advantage of. So let's go in depth on a couple of these. Magnetism. If one compound is magnetic and the other is not, a magnet can physically pull one away from the other, and we can use that to physically separate them. Weight or mass. So one way to separate compounds by weight is to use a machine called a centrifuge, which spins very fast. And it provides an acceleration on these particles, which will be different for particles of different mass. Heavier particles will collect towards the outer edges. Lighter ones will stay near the center. So here's an AI-generated image of a centrifuge, but I think it's basically what centrifuges look like. They're a circle where you can put in different samples, and then it will spin very quickly. And when it really comes down to it, this is kind of the best form of separation, because on the atomic scale, a lot of atoms are only different by their mass, and very small differences in mass as well. You can think of something like uranium-235 and uranium-238 that we might try to separate for nuclear reactors, or hydrogen-1 and hydrogen-2 deuterium. Those are only different by a very small difference in mass, and centrifuging them with very high-powered ones might be one of the only ways to actually separate them. Solubility. If one compound can be dissolved in a liquid, but the other can't, then that liquid can be used to purify both, actually. Also, solids can be separated through filtration or crystallization. Sorry, that word was cut off by the picture. Alright, so you can actually just dump a bunch of liquid on a solid. As long as some part of that solid mixture dissolves in water, you will get some degree of separation as the liquid washes away the part that it can dissolve. But in a more controlled sense, we can do filtration, where you can have a bunch of solid that's sort of in a filter paper. You pass liquid over and through it. The liquid and whatever it dissolves passes through the filter paper, but any solid particles are too large to pass through the small spaces in the filter paper, and they're caught at the top. So I have an image here. It looks almost like coffee, but it's generated by Google Gemini. So this filter is so good, it can even remove like dissolved brown color, which is amazing. I want whatever kind of filter paper they're using. Yeah, just be aware, real filters are not that good. Anyway, we can also use crystallization. So something might dissolve in a liquid at particular volume and temperature, but as you reduce the volume by evaporation or whatever, and maybe reduce the temperature, that usually reduces solubility of solids in liquids, you can start to have those solids come together and crystallize out as a new pure solid. So my image here is supposed to represent sugar crystallizing in water. If you've ever had or eaten rock candy, this is one way that that's made. Then boiling and melting points. Raising or lowering the temperature of a mixture will cause different compounds to change states at different times. Remember, in a mixture, things are not chemically bonded, or at least some of the things are not chemically bonded to each other. Those things can be separated through boiling and melting. So one good way to take advantage of this is through distillation or crystallization, similar to the previous slide I had. But distillation is a type of separation where we're going to heat a liquid up to at least the boiling point of some components of that mixture. Once we reach those boiling points, those will boil off, travel through a tube here, and cool down and recondense or reliquefy in a separate container. You can also use chemical reactions. Of course, different compounds in a mixture will have different chemical properties, so if a carefully selected chemical is added, usually based on prior knowledge of the chemistry between our target and our additive chemical, then only the desired compound in the mixture will react. So one example of using a chemical to separate something from a mixture is again in the uranium refining process. When you go mine uranium ore, you have uranium and its oxides usually mixed with various other silicates or rocks, minerals. And we want to separate that. So there is a reaction with hydrofluoric acid and fluorine that will produce uranium hexafluoride, UF6, which is actually a gas, much more easier to remove. But I don't think these fluorine compounds have the same types of reactions with many of the other rocks and minerals in the ore. And so this is maybe a good way to separate specifically uranium. All right, a little more in-depth detail to some of these processes. So filtration, you're going to have your liquid and insoluble solid mixed together. This might have come just after a recrystallization or a crystallization process. You can pour that into a filter paper. The solid residue will be trapped in the top. Filtered liquid, or the filtrate, travels through into a flask or beaker at the bottom, and then you've separated those compounds. Crystallization. How exactly does that work? So you can dissolve an impure solid, some kind of mixture, maybe various different salts and sugars mixed together. Dissolve that in a solvent. Then you can heat that solvent up. This does two things. It will help everything dissolve, and it will begin to reduce the volume of that solvent. You can then leave it to cool, take it off the burner, and hopefully over time, you might also put it in the refrigerator or freezer even, but be careful not to actually freeze the liquid. Crystals will hopefully start to form, and the cold solution is then poured off, probably filtered again, to be honest, to obtain crystals. Distillation. So here's a more labeled and detailed look at a distillation apparatus. You have your dissolved mixture, put it in a round bottom flask, put a stopper on the top, but have a condenser attached to that. A condenser is a special piece of glassware designed to allow gas to flow through, but also water to flow through around that gas chamber. So there's actually like two areas inside a condenser. There's the open area that's connected to your round bottom flask, but then there's another sort of layer on the outside where liquid water, usually from your sink, can flow through, connected with plastic tubing. But the purpose of having that cold water flow through is it will recondense, reliquefy the gases that you have heated up to the gas phase. All right, so then those condensed liquids will fall into a receiving container, and you've separated the lower boiling point compounds from your original round bottom flask. So distillation can be used for solutions with dissolved solids or a combination of miscible liquids. Miscible liquids are those that can mix together and form a homogeneous solution. So things with different boiling points can be separated with distillation. Then chromatography, specifically paper chromatography. Chromatography is an actual larger unit of this curriculum that we'll study much more in detail later, but just for now, it always has a stationary or a solid phase and a mobile, usually fluid, gas, or liquid phase. So the type that I'm showing you on this slide is paper chromatography. It has a solid paper phase, stationary, and a mobile water fluid phase. So this water will, due to processes of osmosis and adhesion, will travel up this paper. It will overcome gravity even to do so. but it will carry any components that are dissolved in it as well. So different compounds will stick to the stationary phase, the paper, at different rates through intermolecular forces. So your different dissolved compounds in the water will be attracted to the H2O molecules and the paper molecules at different rates. So if it spends more time and sort of enjoys staying in the water more, it will travel farther up the paper. If it prefers or is more attracted to the paper, it's going to stay where it is. So you could imagine we're trying to separate components of an ink here. It's just a black ink to start with, but there may be various colors inside of that as you separate it. You can place a dot of that black ink, place your paper inside a beaker or something. The water, when it makes contact, will start to go up. And then you'll most likely get separation of different dissolved components of that ink mixture. And if your stationary phase is long enough, you can separate compounds. Now, to be honest, this is usually just used for observation purposes, just to see what's in the ink. If you really wanted to separate and reclaim and use different components of this ink, you would have to, I think, use something called column chromatography, which we will discuss later. All right, I just want to give you one example of where various separation methods might be applied. So I've already given you, the example of separating uranium from uranium ore. What about gold as well? People want pure gold, but the separation process for this is quite long and complicated. It begins with various steps here that mostly involve crushing it into smaller and smaller and smaller fine particles, but when it's small enough, near the bottom line there, you start to have chemical processes, addition of oxygen, addition of sodium cyanide, even though it's not written there. Those leach tanks, the leaching process involves a reaction of gold, Au, with cyanide, Cn-, to form different complexes and really dissolve that gold, get it into a homogeneous solution. It will then be mixed with carbon, I think, to stick to different particles of carbon to pull it out of that solution, turn it from more of a homogeneous mixture into heterogeneous. But then it needs to be pulled off of those carbon particles. That's going to happen through a process called electrowinning, I think, where chemical and electrical properties are applied to pull off gold ions from the carbon particles that they're stuck to. Anyway, it's very complicated, but very interesting if you're interested. I'm sure there's YouTube videos or websites about it, but I just wanted to give you one more example of a real long process that uses various types of separation methods. So we can have a summary here. Separation technique: filtration. Mixture is poured through a filter paper, and mixture is probably liquid and solid. So what is removed is the liquid. What's remaining in the filter paper is the solid. Dissolution or dissolving. Your mixture is added to water or some other solvent. What's removed is the soluble substance. So whatever dissolves in the water, you will see it kind of disappear, and whatever is remaining is insoluble in water, remaining solid particles. Crystallization. So we dissolve something in a hot solvent, leave it to cool. The more soluble substances will be removed, they'll not crystallize, and you'll usually throw away that liquid. And what's remaining is the less soluble substances, those that recrystallize into a nice pure crystal. Evaporation or distillation. A mixture of liquids is heated until one compound vaporizes. What's removed is the more volatile compounds, but honestly, that's the one that we're actually going to collect, the removed one this time, because it's far more pure. The remaining is the less volatile compounds, and usually this just remains as like a impure, sludgy mixture of things that don't boil easily. paper chromatography, or chromatography in general, mixture is placed on paper and a mobile fluid phase is allowed to flow. And what's removed is the more soluble compounds. Those will be the ones with the most motion across the paper. They move faster and more distance. Less soluble compounds will stick to the paper and remain near the starting position. So we can try an activity here on the right, how to separate these various mixtures. So imagine a solid mixture of salt and pepper. How might you separate that? You can think about that for a minute. There may be various ways, but thinking about what's efficient, how about dissolving? We could add some water to this. You can think about what these are. Salt is an ionic salt compound. Without knowing what that is really, you should know that salt dissolves in water though, from personal experience, whereas pepper is maybe something that comes from plants. Most of it does not dissolve readily in water, although some of it might, and the pepper that you separate from this mixture probably has a different taste than that which has not been washed with water. Anyway, water-based dyes. We saw one example of this. How about paper chromatography? We can separate dyes based on their interactions between a mobile and stationary phase. 3, sugar and water that are already mixed and dissolved. We could use something like crystallization. We can reduce the volume of liquid through evaporation or boiling, and then we can cool it down in a refrigerator and hopefully get some nice pure sugar crystals. Iron and copper filings. Filings are just very thin sort of strips of this metal. And what if we have iron and copper mixed together? We could try something like magnetic separation. We could pull a magnet over the top of these filings. Iron, being more magnetic, should stick to the magnet, whereas copper will probably remain where it was. So just some ideas on how to think about separating mixtures. Alright. This video is already 44 minutes, so I think I'm going to stop here for this video, but hopefully you've enjoyed learning about the first steps of atoms and chemistry and molecules, and I hope to see you again in the future. Thanks.